Welcome back. In the previous video, we learned the four-step nodal analysis method and applied it to a simple two-node circuit. Today, we use the same method on a richer circuit with a few new twists. First, one of our current sources sits between the two non-reference nodes, not between a node and ground. Second, the question this time asks us to find the voltage across each current source, not just the node voltages. Let's see how the same four steps handle this. Here is our circuit. We have two unknown nodes, V1 and V2. Node V1 is connected to ground through a 2 ohm resistor and to V2 through a 4 ohm resistor. Node V2 is connected to ground through another 4 ohm resistor. Now the current sources. A 3 ampere source enters node V1 from below. A 5 ampere source flows from V1 toward V2. This is the new feature, a source sitting between two non-reference nodes. And a 6 ampere source enters node V2 from below. Our goal: first find V1 and V2, then find the voltage across each of the three current sources. Let's write KCL and note V1. 4 terms this time. First, the 2 ohm resistor to ground gives V1 over 2. Second, the 4 ohm resistor to V2 gives V1 minus V2 divided by 4. Now the sources. The 3 ampere source is entering V1, so by the entering-leaving rule, we write minus 3. The 5 ampere source is leaving V1 toward V2, so we write plus 5. Putting it all together, V1 over 2 plus V1 minus V2 over 4 minus 3 plus 5 equals 0. Multiply through by 4 to clear denominators. We get 2V1 plus V1 minus V2 plus 8 equals 0. Combining like terms, 3V1 minus V2 equals minus 8. That is our first equation. Now KCL at node V2. Again, 4 terms. First, the 4 ohm resistor to ground gives V2 over 4. Second, the same 4 ohm resistor we saw before, but now seen from V2, gives V2 minus V1 divided by 4. Now the sources. The 5 ampere source is entering V2 from V1, so we write minus 5. The 6 ampere source also enters V2, so we write minus 6. Putting it together, V2 over 4 plus V2 minus V1 over 4 minus 5 minus 6 equals 0. Multiply through by 4, we get V2 plus V2 minus V1 minus 44 equals 0. Combining, minus V1 plus 2V2 equals 44. That is our second equation. Now we solve the two equations together. Equation 1. 3V1 minus V2 equals minus 8. Equation 2. Minus V1 plus 2V2 equals 44. This time we'll use substitution. From equation 1, V2 equals 3V1 plus 8. Substitute into equation 2, minus V1 plus 2 times the quantity 3V1 plus 8 equals 44. Expanding. Minus V1 plus 6V1 plus 16 equals 44. 5V1 equals 28. So V1 equals 5.6 volts. Now back substitute. V2 equals 3 times 5.6 plus 8, which is 24.8 volts. Quick check at node V1. 5.6 over 2 is 2.8. 5.6 minus 24.8 over 4 is minus 4.8. Add the source terms. Minus 3 plus 5 gives plus 2. Total, 2.8 minus 4.8 plus 2 equals 0. Our solution is correct. Now, the second part of the question. Find the voltage across each current source. We use Kirchhoff's voltage law, which simply says the voltage across any element equals the difference of node voltages at its terminals. The 3 ampere source sits between V1 and ground, so its voltage is V1 minus 0, which is 5.6 volts. The 5 ampere source sits between V1 and V2, with current flowing from V1 toward V2. Its voltage is V2 minus V1, which is 24.8 minus 5.6 equals 19.2 volts. And the 6 ampere source sits between V2 and ground. Its voltage is V2 minus 0, which is 24.8 volts. Notice the sign convention. The plus terminal of each source is on the side where the current exits. 3 takeaways from this example. First, the same 4-step nodal method works even when a current source sits between 2 non-reference nodes. Just write the source on both nodes' equations with opposite signs. Second, once you know the node voltages, the voltage across any element is simply the difference of the node voltages at its terminals. And third, the plus terminal of a current source is always on the side where the current exits the source. In the next video, we'll tackle a 3-node example.